Honestly, I
And you get paid.
imagine.
But you have to do it again.
You go into the big things, you know, everyone's like, time to get fed.
So far, a lot of people getting infected during the lineup buying the mask. It's like, hey, how much is it?
Okay, so before we start today, does anybody have any questions for me? All right, so last class we looked at this notion of conditional probability, where you write things like this, which you read as the probability of A given B, and you interpret sort of in your mind as if I run the big experiment that has any possible outcome in the set S, but I tell you that the outcome was actually in the set B, what do you then know about the probability of A knowing that this thing in the set B happened? And this is very related to today's topic, which is independence. And independence basically means that if I tell you that the event B happened, it doesn't really give you any information at all about whether A happened. But that's not the definition, although some people might think that. It's almost the definition, but here is the actual definition. Two events, the definition is actually simpler. A and B are independent if the probability of A, well, let's write it this way, the probability of A and B is equal to the probability of A times the probability of B. So this is, let's remember, it's the definition of what it means for two events to be independent. So if someone says, prove to me that the events A and B are independent, then what you have to prove is that the probability of A and B is equal to the probability of A times the probability of B. On the other hand, if someone tells you that the events A and B are independent, then the definition is really helpful, because from it you can read off a formula for the probability of A and B. Somehow there's a divide and conquer formula you can use, which is this sort of complicated thing that involves two events. I can break it down into knowing what the probability of A is and knowing what the probability of B is, and if they are independent, then this will be the probability that they both happen. There's one consequence which sometimes people also treat as the definition. If A and B are independent and the probability of B happens to be bigger than 0, then the probability of A given B is equal to the probability of A. So why is that? Well, we can just write this out longhand. The probability of A given B, remember the definition of this is the probability of A given B is equal to the probability of A and B divided by the probability of B, which, if A and B are independent, then the probability of A and B is just the product of these two probabilities. And the probabilities of B cancel out. So the probability of A given B is just the probability of A. This definition is a little bit more useful. So they're almost equivalent. This one's just slightly more useful because here you have a division happening by the probability of B, which means this only makes sense if the probability of B is bigger than 0. This makes sense, doesn't matter. Either probability of A or probability of B can be equal to 0, and this still makes sense. Okay? So it's clear what the definition is. All right, so let's test it out. See if it gives us the sort of intuitive results that we expect. So let's do classic example. Rolling 2 dice. So here you have a set of possible outcomes, which I'll call D1, D2. Maybe D1 is the red die, D2 is the blue die, and each of those is an integer in the set 1, 2, 3, 4, 5, 6. And the probability function over this thing is that the probability of any particular outcome, so that means that the red die has some particular value and the blue die has some particular value, is just 1 over the size of S, which is 1 over 36. And why 36? Because there are 6 choices for this and 6 choices for this. Okay. So that's the setup. And let's define a couple of events. Let's say A is the event, D1 is equal to 4. And so what does that look like? That looks like, so this is the way I write it in sort of plain language, but of course an event is always a subset of this space. So that's just these outcomes. And let's take B to be the event. D2 is equal to 3. And what does that look like? That's 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, and 6, 3. All right. What does your intuition tell you? Are A and B independent? So I roll 2 dice. One of them asks the question, is D1 equal to 4? The other one asks the question, is D2 equal to 3? Do you think that those are independent?
Yes.
Seems like it, right? I mean, if I go into the other room and roll the blue die, and then I come back here and roll the red die, somehow that shouldn't, I mean, what had happened in the other room shouldn't have any effect on what's happening here with the blue die in this room, which, well, if I roll them together, then that also shouldn't make a difference. So intuitively, they should be independent. But the only way to know this for sure is to check this. So let's check it. So we need to know 3 quantities: probability of A, probability of B, and probability of A and B. So let's look at those 3 sets. What is the set A and B? How big is that set? Subsize 1. And what's in it? So this is one of those questions that is too silly to answer for some people and impossible to answer for others. So what's in the set? So if it's really easy for you, tell me what's in the set.
4-3.
4-3. There's exactly one thing that's common to those two sets. 4-3. Let's just see that. Here is 4-3 in A, and here is 4-3 in B. And indeed, if you check really carefully, you'll see that there's nothing else that's in both of those sets. So A intersect B is just this one thing, 4-3. All right. So, so then the probability of A and B is what? Yep. 1 out of 36 because there's only one element in there. So that's 1 out of 36. And what's the probability of B? Yep. So it's the size of B divided by 36, which the size of B is 6, which is 1 out of 6. And the probability of A is equal to the size of A divided by 36, which is also 6 over 36, which is still 1 over 6. So now we need to test the definition. The probability of A and B is equal to 1 out of 36. The probability of A times the probability of B is 1 out of 6 times 1 out of 6 is 1 out of 36. And indeed, these two things are equal, so A and B are independent. So that seems to work, and it gives us the answer that we expect. Now, quick note about terminology. So this is what it means for A and B to be independent. If A and B are not independent, then just say that they are not independent. So don't say they're dependent, or A depends on B, or B depends on A. Just say they're not independent. All right, so that's one example. Let's try another one of these. So let's take B now and change it, and let's say actually B is the event D1 plus D2 is equal to 7. So A stays the same, D1 is equal to 4, B is D1 plus D2 is equal to 7. Are these, do you think A and B are independent? Now it's kind of looks like they're not, or at least it's not obvious that they are, right? Before, A just depended on the value of D1, and B just depended on the value of D2, and we had this nice argument, well, what happens to D1 has nothing to do with what happens to D2, but now we have B that depends on both D1 and D2, and A depends on D1, so both of them kind of depend on the same at least partially on the same thing. So there's no reason to think immediately that they're independent. So do we conclude that they're not independent? We can't conclude that because definition of independence doesn't ask whether or not A and B depend on the same thing. It asks whether this formula is true. So we have to check if this formula is true for these two particular events, A and B. So let's check it. And for that, we've seen how we can do that for things like this. We'll just explicitly write out what A is and what B is. We're already halfway there because we already know what A is. So let's write what B is. Okay, so these are the outcomes where I roll 2 dice and I add them up and I get 7. So that looks like 1 and a 6, looks like a 2 and a 5, or a 3 and a 4, or a 4 and a 3, or a 5 and a 2, or a 6 and a 1. That's all the ways to get 7, right? It's basically all the ways you can roll the 1, the first dice, and then after that, the second one has to be the specific value to add up to 7. Okay, so we want to test independence. That means we need to know what is the set A and B. So we say it out loud. The first thing I roll is a 4, and then the sum of both of them is 7. That's the way we say it out loud. But as a set, what is that thing?
4, 3.
Yep. So looking up in A, this adds up to 5, this adds up to 6, this one adds to 7, so actually it's also in B. But this is 8, this is 9, this is 10, so none of those are in B. And that's basically the only thing from A that's in B is 4, 3, and it's actually in B. So that means A and B is equal to set with one element, 4, 3. But now, we kind of know what's going to happen now because we did this already. Probability of B is the size of B over 36, which is 6 over 36, which is still 1 over 6. The probability of A and B has only one element in it, so that's 1 over 36. So probability of A and B is 1 over 36. The probability of A times the probability of B is 1 over 6 times 1 over 6 is 1 over 36. So these two events are actually independent. So, again, this is one of the things about probability theory because it tends to talk about things that we think we understand, that we have knowledge of. And it uses these natural words like independence and events that we think we get, but if someone asks you a question, a really well-formed question about some probability question, then you have to go to the definitions and see what the answer to that question is. And in this case, I think most people here thought, well, no, these things can't be independent because they both depend on the value of D1. That's not true. And that's why I don't like to use words like A and B depend on something. Either they're independent or they're not independent. And independent means exactly this, and it means only this. Okay. So we've seen two examples where they are independent. Let's try one where that's not necessarily the case. We'll back it up. And we'll change B yet again. And instead of making B add up to 7, somehow we already saw for dice, 7 seems to be adding, when you roll 2 dice and add them up, 7 is kind of a magic number. It was the one that was most likely to occur, so let's change it to something else. Let's try, well, what if I say B is the event that those 2 dice add up to 5? Then we can write it out explicitly. So do you think these are dependent or independent now? Do you think they're independent or not independent? Yes. So who thinks they're independent? And who thinks they're not independent? Okay. So the majority has it, so we don't need to do the calculation. Not independent is the answer. You don't get to vote, or at least the voting doesn't determine the truth of the statement or not. So we just need to write it out. If you want to add up to 5, you can roll a 1 and a 4, or you can roll a 2 and a 3, or you can roll a 3 and a 2, or you can roll a 4 and a 1, and that's it. And now something has changed here. What has changed is the size of this set is not 6 anymore, it's only 1, 2, 3, 4. Let's remember that. And we need to know A and B. Okay, what is the intersection of A and B in this case? There it is. 4 and 1. This is the only thing in here where the first thing is a 4. And there it is up there. So A and B is 4, 1. So now we have probability of B is the size of B over 36, which is 4 over 36. I'll leave that the way it is. It's actually 1 over 9, but it doesn't matter. And the probability of A and B, well, A and B still only has size 1. So it's a 1 out of 36. So let's check our calculations up here. Probability of A and B is 1 out of 36. Yes. Probability of A times the probability of B. This is 1 over 6 is the probability of A, but the probability of B is 4 out of 36. And I don't know what that is, but I know that it's not equal to 1 out of 36. So in this case, A and B are not independent for these 2 particular events, A and B. All right. So here's a pretty basic property of independent events. It shows up in the textbook. I'll write it here as a lemma. If A and B are independent, then A and not B are independent. So let's think for a second about what this means. So intuitively, A and B are independent means if I tell you B happened, then you didn't really learn anything about whether A happened. So it stands to reason that if I tell you B didn't happen, you shouldn't really learn anything about whether or not A happened. That sounds reasonable, right? But again, things that sound reasonable are not always true. So let's just check it. So what do we want to show? We need to show that the probability of A and not B is equal to the probability of A times the probability of not B, which is the same thing as saying that the probability of A and not B is equal to the probability of A. And do we have another way of writing the probability of not B? Yeah. Right, this is, that by the complement rule, this is equal to the probability of not B. So that's what we need to show. So let's do a Venn diagram. We have A and we have B. Here we have A and not B, right? Inside this region of the Venn diagram is the stuff that is in A, but it's not in B. And here we have the stuff that is in A and it's in B. So that tells us that the probability of A, we can write that as the probability of A and B plus the probability of A and not B. This probability plus this probability. No cheating there. All right. Well, the lemma is a question about what do we know if A and B are independent. Then we're trying to prove that A and not B are independent. So we know A and B are independent. Does that let us do anything to this formula here? We have probability of A and B in this formula, and independence means that that's the probability of A times the probability of B. And we still have the second part. All right, so then yeah. So what do we got here? Let's rewrite this a little bit. So on the left-hand side, we have probability of A. On the right-hand side, we have probability of A times the probability of B. So another way to say that is to isolate this part. So that's the same thing as saying probability of A and not B is equal to, we've got this thing, probability of A, and we need to subtract, bring this thing over, so that's minus the probability of A times the probability of B. All right, what's that? Well, on this right-hand side, we have probability of A as one of the factors in here. Probability of A is also a factor in here, so let's bring that out. So that's just the probability of A times 1 minus the probability of B, right? Probability of A times 1, probability of A minus the probability of A times B. And we're done. we needed to show that the probability of A and not B was equal to the probability of A times the probability of not B. And what we we argued that that's the same thing as showing that that's the probability of A times 1 minus the probability of B. And now we have it. Probability of A and not B is probability of A times 1 minus the probability of B. So the thing that seemed reasonable, that if telling you about B doesn't tell you anything about A, then, so telling you B happened doesn't give you any information about A, then telling you B didn't happen shouldn't give you any information about A. And it doesn't. All right. Here's where things get hairy. So people understand the definition now of what it means for two events to be independent. Okay. And now there's this idea we can keep in our back pocket that if two events are independent, then somehow their complements are also independent. But that tells us what it means for two events to be independent. What about more than two events? And here's where things get messy. And just so that I don't here's the definition. Let A1, A2, up to AN be a sequence of events. So again, there's some unfortunate language here. So a sequence of events just means a bunch of subsets that are listed one after the other. The reason we say sequence instead of sets has nothing to do with the events happening one after the other. There's no notion of time in probability theory here. It just means it allows us that maybe actually one of the same event appears twice in this list, which we can't say set and have that be true. So A1 are a sequence, A1 to AN are a sequence of events. Then, so what does it mean for these things to be independent? Well, I know what it means for two of them to be independent. But what about a whole bunch of them like this? And it turns out that there's actually no natural or fully agreed upon definition. The definition that you use depends on exactly what you need from them. Here's one of them. Then A1 through AN are pairwise independent. If probability of AI and AJ is equal to the probability of AI times the probability of AJ for every distinct pair of indices ij taken from the set 1 through n. So there's one definition, and it just relies on the fact that we have a nice clean definition of what it means for two events to be independent. So if you ask me about a whole bunch of events, well, I just look at every pair of them and check if they're independent. And if so, then I'll say that that whole sequence of events is pairwise independent. An alternative definition, and which is much stronger, we say that A1 through AN are mutually independent if for every k in 2 up to n, and every 1 less than or equal to I1 less than or equal to I2 less than or equal to, and so on, all the way up to Ik less than or equal to n, the probability of AI1 and AI2 and AI3 and so on, all the way up to AIK is equal to the probability of AI1 times the probability of AI2 times, and so on, all the way up to times the probability of AIK. So, second definition of what it means for a bunch of events like this to be independent, and it's a much stronger definition, says that I should be able to take any subset of these events, as long as there's at least 2 of them in the subset, and the probability that all of them happen is equal to just the products of those individual probabilities. So is that clear? So it's probably not clear how you apply this thing or how you prove this kind of thing. And indeed, that's because it's difficult, typically. So in particular, if I give you a bunch of these things, these events, A1 through AN, and you want to check if they're pairwise independent, you need to look at every pair. So just to test this definition, how many pairs of events are there? Well, if there's n of them, there's n choose 2 pairs. So that's like, n times n minus 1 over 2. So that gets big pretty quickly. If you want to test this definition, what is this definition doing? Actually, it's going over all the subsets. So you need to check every subset of events except for the subset of size 0, because it doesn't make sense to ask that, and the subsets of size 1, because, again, those don't make sense, right? You need at least 2 things for this formula to make any sense at all. So you have to check this for, well, the number of subsets of n elements is 2 to the n, but you don't have to check the sets of size 1, so that saves n of them, and you don't have to check the set of size 0, so that saves 1 of them, but this is still enormous, right? If you have 32 of these events and you want to check this, this is about 4 billion. So not what we're going to do on the board today. And if you have 32 here, this is also not great, right? I mean, this is still a big number. So usually you don't have to work with, you don't have to prove these things quite in this way. Sometimes you can manage to prove pairwise independence for certain particular setups, but this mutual independence, usually it comes from the problem statement. So, and that's, the problem will say, I perform n mutually independent coin tosses. That's what you're working with, and so then really mutual independence is nice because it means you give me any subset of those coins and ask me any question about them, then I can know the answer. Use this to figure out the answer. If you end up having to do this by the definition, by enumerating everything, it had better be a small set, like a set of size 3 maybe. And we've seen this kind of problem before. Actually, we saw this, for example, with the principle of inclusion-exclusion. You saw that with the principle of inclusion-exclusion, what's the size of A union B? That's this thing that has 3 terms. What about the size of A union B union C? Well, that has more terms in it. And what about the size of A1 union A2 union all the way up to AN? That's the thing that has 2 to the n terms in it. So we've run into these kinds of problems before. Okay. So let's check a baby. One example with 3 different events. See if we can do it. The example is going to be a random bit string of length 2. That's a nice easy one. That means our set S of possible outcomes is 0, 0, 0, 1, 1, 0, or 1, 1. And I'll define 3 events. A is the event. So another way to write that is to call this B1, bit 2, such that B1, B2 is in the set 0, 1. That's the same, another way of writing this set, but I like to have names for these 2 things. So the first bit is B1, the second bit is B2. So let's say first event is B1 is equal to 1. So one of the events is, well, the first thing is equal to 1. Second event is B2 is equal to 1. And the third event will be B1 is not equal to B2. There's 3 events defined over these bit strings, and these are supposed to be uniformly random, so that means the probability of any given bit string is going to be 1 out of 4. 3 events. B1 equals 1, B2 equals 1, or B1 and B2 are different. So those are the 3 events. Do you think that those things are mutually independent? Do you think they're pairwise independent? There's only one way to find out. So for pairwise independent, let's start with that. Let's compute the baby probabilities. So the event A has B1 equal to 1. So that's going to have a 1, 0 and 1, 1. The event B has B2 equal to 1. So that's going to have a 0, 1 and a 1, 1. And the event C says B1 and B2 are different. So that's going to have 0, 1 and 1, 0. Okay? Everyone agree? I haven't made any mistakes? So what's the probability of A? Yep. 2 over 4, and so that's 1/2. And that's also the probability of B, and that's also the probability of C. All right, so the definition of pairwise independence says that we need to check for every pair of events whether or not this holds. So let's do it. Probability of A and B. What's A and B? A and B is this and this. What's common to those two things? Anything? Yeah. That's just the probability of 1, 1. That's the only one that occurs in both of them. So that's going to be 1 over 4. And look at that. That's actually equal to the probability of A times the probability of B. Probability of B and C is the next thing we need to check. We need to try all three pairs. So what do B and C have in common? That's 1 over 4. And look at that. That's equal to the probability of B times the probability of C. And then we need to check the last pair is A and C. A and C, I see a 1, 0 here and a 1, 0 there, but neither of these ones. So that's just the probability of 1, 0, which is 1 over 4, which is equal to the probability of A times the probability of C. So we have 3 events. For every pair of them, AB, BC, and AC, we checked, and that pair was independent. And so we conclude that A, B, and C are actually pairwise independent. Are they mutually independent? Who thinks yes? Who thinks no? I mean, who would have thought that they were pairwise independent even? I mean, that already seems crazy because there's so little going on here, and C depends on both of them, but somehow it managed to work out. Think they're mutually independent? If you don't, can you give me a very quick reason why? What's that? Yeah. So we're not far off from actually having completely checked mutual independence here, because mutual independence starts by checking all the pairs and then all the subsets of size 3 and all the subsets of size 4, but we only have 3 things, so we only need to check one more thing. And the thing we need to check is the probability of A and B and C. But if we look at those, okay, 0, 1 is in these two, but it's not up here. And 1, 0, well, that's not here. So actually, A and B and C is the empty set. And the probability of the empty set is an empty sum of probabilities, which is 0. On the other hand, that is not equal to 1/8. And 1/8 is the probability of A times the probability of B times the probability of C. So the conclusion here is A, B, and C are pairwise independent, but A, B, and C are not mutually independent. So the two definitions differ already even for a set of size 3. Easy example there. Okay. So I said a lot of these probability lectures finish with a surprise. So let's see if we can have a surprising result today. Just check my probabilities. So we have 3 students, Annie, Boris, and Charlie. Are writing a 1-question true or false exam. So they have a really bad professor who writes a final exam that consists of 1 question and it's a true or false answer. Okay. So Annie and Boris are actually fairly good students. Okay. So Annie answers correctly with probability 0.9. So Annie's practiced on a lot of these exams in the past, and 90% of the time she gets the right answer and gets 100% on the exam. Boris is also a clever student, and he answers correctly 90% of the time. But poor Charlie, he doesn't do so well. He only answers correctly 60% of the time. Okay. Okay. And maybe all right, you understand the setup? So what I'm interested in is the following question. What is the probability that at least 2 students answer correctly? That's still too easy. Because there's 2 ways that this exam can play out. Everybody knows who is a good student and who is a bad student. In particular, Charlie knows that he is not as good as Annie or Boris. And so, option 1, Annie, Boris, and Charlie write the exam independently. Okay? That's what you would expect. They each go off to their own parts of the room, very far apart, each write the exam. Annie succeeds with probability 9 out of 10, Boris succeeds with probability 9 out of 10, Charlie succeeds with probability 6 out of 10, and those 3 events, which I will call A, B, and C, are independent, mutually independent. Option 2, Annie and Boris write independently, but Charlie copies Annie's answer. So in this scenario, looks better for everyone. Annie's still getting it right 90% of the time. Boris is still getting it right 90% of the time. Charlie is not using his brain, but he's going to get the right answer 90% of the time. I mean, this certainly looks like the better thing for everybody, right? So, I would like to compute the probability that at least 2 students answer correctly under both of these alternatives, or under each of these alternatives. So, let's start with the fair test situation where everybody writes their own exam. Okay? So, I'm interested in probability that at least 2 of them answer correctly. So that is equal to, let's go to our Venn diagram. A, B, and C. So 2 of them answering correctly, at least 2 of them answering correctly, that's this part in here, right, where there's at least 2 circles overlapping. So if I want to know what that probability is, that's going to be probability of A and B, there, plus probability of B and C, that's the blue thing, plus the probability of A and C, that's the purple thing. And is that what the total probability is? Is that the correct answer now? No. What's wrong? So there's some extra counting going on here, and in particular there's this region here which is counted not once, not twice, but 3 times. And I only want to count it once. So I will need to subtract that part in the center, which is A and B and C. Yeah? Okay. So now we're assuming in this scenario that everybody writes the exam independently, and so the events A, B, and C are mutually independent, which will let us compute all of these things. So that means that this is probability of A times probability of B. This one is the probability of B times the probability of C. This one is the probability of A times the probability of C. And this one, oh, sorry. You should stop me when I make these mistakes. You need to subtract 2 times A intersect B intersect C. We counted this part 3 times. We only want to count it once, so we need to subtract 2 times that probability. Minus 2 times probability of A times probability of B times probability of C. Okay, Annie and Boris, they're the clever ones. So this is 9 out of 10 squared. This is, Boris is the clever one. Charlie, not so much. This is Annie and Charlie, again, clever one, but not so much. Minus 2 times 9 out of 10 squared, 6 out of 10. So now you pull out your Python interpreter, calculate that, and what you get is 459 out of 500. And that's 0.918. Okay. So in this scenario, at least 2 of them get the right answer about nearly 92% of the time. So that's already that's already really high, right? And that's where they don't cheat. So imagine how good it's going to be when Charlie decides to cheat. They're going to do great then, right? So this was under option 1. Now let's look at option 2. In option 2, there isn't really an event C anymore. I mean, C and A are the same thing. Charlie is copying Annie's answer, so really whatever we do to figure this out, it really only depends what Charlie answers, what Annie answers, and what Boris answers, because Charlie's just going to copy Annie's answer. So the Venn diagram in that picture has whatever Annie's doing, whatever Boris is doing, and Charlie's just going to do the same thing. So in this picture, how do I get 2 students, at least 2 students, to have the correct answer? Yep. Annie has to get it right, and Charlie has to get it right. No, that's not true. Annie has to get it right. Annie has to get it right, actually, is the only thing. Right. If Annie gets it right, 2 people get the right answer. Annie and Charlie. If Annie gets it wrong, 2 people get the wrong answer. So the only thing that matters is whether Annie gets it right. So in option 2, 2 people get the right answer. In fact, at least 2. If and only if Annie gets the right answer. But that's just the probability of A. And that's 9 out of 10, which is 0.90. So in this second scenario, which seemed like it was better for everyone, it's actually less likely that the majority of the class will pass the test. In fact, it's more likely that the professor will see 2/3 of the students fail the course under that scenario. And, you know, you guys can test that out yourselves. No, I mean, you can also test it out as a mind experiment, where, you know, I'm interested in, you know, I'm of course interested in how many people succeed in this class. So you guys can, in particular, what fraction of the people succeed in this class. And so, I mean, imagine you all go and you write the final exams, each independently. What will almost surely happen is some reasonable number of you will pass and some other number of you will not pass. Versus the other option is you elect one person in this class to write the final exam for all of you, and see what happens there. So it's almost, I'm certain in this class I'm going to get approximately the same number of people that happen every year will pass the final exam, plus or minus a couple of percent. On the other hand, if you elect one person, then that person has a bad day, then you all fail. So nobody passes. And that's much more likely to happen than for, you know, 3/4 of you to have a particularly bad day on the final exam. So on the other hand, Charlie's not interested in whether the majority of the class passes or fails, right? Charlie's interested in one thing, which is whether or not he passes. So this is still an advantage for him to do this. Okay. So, short lecture today. If you have questions for me, you can put them